Okay. Now, let's take the limit. Let n go to infinity. Let n go to infinity. What happens? What happens to the n? Well, you get the limit. E to the c is just a positive, it's just some number, right? So you get the limit of x to the n plus 1 over n plus 1 factorial as n goes to infinity, right? And what is that? We saw this earlier. What's the limit of this? Does anyone remember? We saw the limit of this. What's the limit? For any x, it actually turns out to be 0. This is something we did earlier. Okay. Okay. So what does that tell you? So the limit from r sub n is 0 as n goes to infinity. Okay. And so that tells you that, in fact, e to the x really is this power series. Okay. It really is it. It's not just, this isn't just the power series that you get. It actually recovers e to the x. Same thing for the sine. Same thing for the sine, right? How do we know that x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus blah, blah, blah? Why does this recover the sine function? Does this recover the sine function? Again, we look at the error, right? The error is going to be, right, the n plus 1th derivative of the sine, right? So the n plus 1th derivative of the sine evaluated at some point over n plus 1 factorial times x to the n plus 1. Right? But that tells us that the absolute value of that is smaller than 1 over n plus 1 factorial times the absolute value of x to the n plus 1. Right? Same as before, the limit, when you take the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, you get 0. Since that equals 0, we know that the limit by the squeeze theorem, the limit of the error is also equals to 0. Okay. So this is the series for the sine, right? So the sine, this series actually recovers the sine. Right? Okay. So we gave one example. So we gave one example of where the Taylor series messes up, right? The Taylor series gives you a function that's not your original function, okay? But in these two examples, at least, we're good, right? The Taylor series actually does recover the original function. Any questions on what we just did? Okay. You see how this works, right? You have your function, you have your Taylor series, you have the error. Okay. The Taylor series might not recover your function, but if you look at the error term, if you can see that the error term goes to 0, then it does recover your function. Okay, and that's the game we're playing here. Here we see that, you know, for any x, the error goes to 0. Great. This series works everywhere. Same thing here. You know, the error term for any x, the error term goes to 0. Great. This series recovers your function on the whole line. Okay, so that, going backwards to what I was trying to do at the beginning of class. Do you remember at the beginning of class I said, oh, let's do this, and I said, oh wait, we don't have any examples. Now we can do some examples of multiplication, integration. So we know at this point e to the x actually equals x to the n over n factorial on the whole line. We also know that sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus blah 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 for the whole line. Okay, so this is, let me write it like this. You get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus blah 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 for x and r. Okay, so e to the x sine x, you can actually work out by multiplying just like you multiply polynomials. So we can multiply the series like polynomials, just like we had polynomials. Okay. So we are going to get what? We're going to get x. We're going to get an x squared, right? How many x cubes do we have? Well, we have minus 1 over 3 factorial x cubes from here, but we have plus 1 over 2 factorial x cubed, right? How many x fourths do we have? We have x to the 4th, we have 1 over 3 factorial x fourth here. We have minus the same thing. So we have no x fourths. X to the 4th, right? How many x to the 5th, etc., etc. Okay. I hope you see what I'm doing, right? I'm just multiplying these guys as if they were polynomials, right? Okay. So that's the moral, that if you have power series that converge, then the product is going to have the power series of the product is going to be the polynomial multiplication product of the power series. Okay, you just multiply them just like they were polynomials. Okay. The same thing is actually true for division. If you want to find the power series of this over that, then you would take one power series and you divide it by the other power series, just like they were polynomials again, and you work that out. but it's kind of a pain, so I don't want to do it. I'm not going to do it. Look in your book. There's an example. In the book they give an example of finding the power series of tangent, and the way they do it is they take the power series of sine and then divide it by the power series of the cosine, and you get the power series for the tangent. Let me give another example, integration example. Okay. The integral of e to the negative x squared dx, and this is also from your book actually. Integral of e to the negative x squared dx. Okay. Can anyone do this using some trick? The answer is no. It's not so easy to do. Yeah. If you try, actually, there's no way to get a simple elementary expression for this. Let me just scare them away. I guess I didn't scare them away. Okay. So if you want to integrate this, actually it's not possible to use, like you hope you could use the fundamental theorem of calculus, but what's the antiderivative? There's no simple antiderivative. I'm sorry, if you were trying to integrate a definite integral, you try to find an antiderivative. There is no simple antiderivative of this. Okay, but at this point, we're good. We can do something good, which is we say, oh look, e to the negative x squared. Well, remember, e to the x is summation x to the n over n factorial, right? For all x, right? So let's just substitute in negative x squared into here, okay? Right, and we get summation negative x squared to the n over n factorial from n equals 0 to infinity. Right? In other words, we get summation negative 1 to the n x to the 2n over n factorial from n equals 0 to infinity. Okay, and so we get, we have this power series expansion of e to the negative x squared that works for all x, right? This works for all x in R. Okay, and now at this point we use the integration theorem that said that integrating a power series means just taking the sum of the integrals of each term. That you can do term-wise integration. So we know that this equals negative 1 to the n x to the 2n over n factorial from n equals 0 to infinity dx, right? But in fact, we can do term by term integration, right? So we say, okay, this is just the sum of the integrals of negative 1 to the n, x to the n, x to the 2n over n factorial dx, and from 0 to infinity, which turns out to be summation negative 1 to the n, x to the 2n plus 1 over n factorial 2n plus 1. And from 0 to infinity. Okay. So if this question So this problem was basically impossible before. But once you have the theory of power series, then it's a very simple answer, right? You can get the answer, here it is. It's expressed as a power series. and this power series is valid on the whole line. Okay, so at one point in history, they felt like this is great. We can solve everything using power series. That turned out to be not true, but at least in some sense, power series allow you to do a lot more things than you could before. Okay, that's it for today.